Yeah, Arnab, can you confirm you're there? Arnab, can you do a quick sound check?
Hello.
Yeah, Arnab, you're a little low. Can you be a little loud?
Okay. Hello.
Yeah, this is much better.
Okay.
Thanks. Andre, can you do a quick sound check?
Yes, sir. I'm here.
You're still low. You need to be a little high.
Hello.
Still very low.
Hello.
No, you need to be a little more loud.
Okay, sir. Hello. Sir, is it okay now?
It is not. Okay, good evening, everyone. It is 4 minutes past 7:30. Our allotted time to start this repeat session of faculty development program of AIORI 3. Can I request the first slide of the slide deck for today's evening to be projected on the screen?
Yes, sir. I'm sharing the screen. Just one moment. I think I'll be needing the permission to share my screen.
You have that now.
Yes. I hope my screen is visible.
Yes, it is. So, good evening, everyone, to the repeat session of AIORI 3 Faculty Development Program, Session 1. Just to give you a mission statement for AIORI 3, it is to conduct annual skill development workshops and hackathons that strengthen India's internet infrastructure resilient and build a self-reliant supply chain of technical talent, limiting the country's exposure to externalities. What essentially this mission statement for AIORI 3 means that we are going to do this skill development program year after year, And the objective is to create a supply chain of the technical talent by identifying the sparks and then handholding them for them to move on to the next stages of contribution and then finally become an active community member of this internet ecosystem. Now, AIORI 3 is not the first year where we are doing this. The AIORI 3, as you can see, that it is the third edition, and this third edition is happening in 2026. So the first two editions which happened were in 2024 and 2025. Now, if you can see my screen, the first edition AIORI 1, we focused on internet standards, measurement, and research engagement. And in this edition, which happened in 2024, we partnered with IEEE IAYPC, and we did student workshops at 5 different locations across India, wherein approximately 250 participants, participations, students participated. Sorry for that, participated, and then from there on, we did hackathons. We had 5 problem statements, and there was an online hackathon followed by a physical hackathon. Out of the online hackathon, 23 teams which uh, did exemplary job were taken to the next round of physical hackathon, where we supported all the teams to reach to their to IIT Guwahati, where the physical hackathon took place. Out of which 9 top teams were selected, and then finally 5 teams made it to the finals. Uh, Out of which uh, the 2 teams which were the best performing teams, we even supported them to go to IETF 122, which happened in Bangkok. Now, this was our AIORI 1. Now, if you want to see what happened there, these are the universities, these are the pictures which you can see. It is available on our website. Now, we from here onward, we moved to AIORI 2, which was in 2025. Herein, we pivoted ourselves on the faculties rather than the students. So here, last year during the same time frame, we did regional faculty workshops. These workshops were done at 11 locations, wherein 293 faculty members participated. And then each one of the faculty members were requested to do a student workshop in their own location, in their own institution. So it happened at 50 locations, and approximately 1,500 students participated in the same. From therein, we did a call for hackathon, and this call for hackathon again had 2 parts: remote and physical. In the remote hackathon, we selected 53 teams. We mentored those teams, out of which the top 23 teams were again taken to Chandigarh University this time, where the physical hackathon took place. Now, this was AIORI 2. If you want to see that what are the contribution of these top 23 teams are, it is all available here. The details of the champion teams are also mentioned here, what they did exactly. And if you want to see that what are their exact codes and contributions, that is also in this website. If you click here in the physical hackathon, it will take you to the page where all the details are there. So this is the physical hackathon page. So for each one of the participating teams, you can see their GitHub repository, the PowerPoint slide deck which they presented, and the PDF of their work. everything is available on this website. Now, this was our second edition. In the third edition, which is currently ongoing, we have again changed this a little bit. This time we are partnering with ISEA. It is a Government of India initiative on information security, education, and awareness. AIORI is also a Ministry of Electronics and Information Technology supported program. So these two programs have come together. This The phase and the timeline is as follows. From 58 to 38 June, we requested expression of interest for faculty to conduct a workshop at your own institute. We have received an overwhelming response to that. And then this is the time frame where we are running the faculty development program. And we did the first session on Wednesday, and this is the repeat session which is happening today. This is happening in this month. Now, once this is over, we will have an AIORI workshop wherein you are requested, you will have to organize the workshop at your own institutes, for which there is also a token remuneration associated for the SPOC faculty. Once that is done, we will give a call for hackathon from 16th to 30th September. Online hackathon will be from 1st October to 31st October. Regional hackathon will happen from 1st November to 30th November. Like the national hackathon last time, we are now having regional hackathons where it will be easier for teams to come and participate. And then the winning teams from each one of the regional hackathons will move on to the national ISEA conference, which is happening at IIT Jammu in the month of December. So this is the timeline. Currently, we are at this stage of faculty development program, and welcome to all of you. Some of you who could not join the last session, the previous session which happened on Wednesday, or some of you might have thought to rejoin it. Whatever is the case, I welcome you all once again to this session. Now, if I can stop my share and request Arnab to pull up the slide deck again. So broadly, what we would like to share now is that how the next 1.5 hours is going to be structured. So this is the inaugural session which is happening. The initial time I have taken to take you through what is in it, what has happened earlier, and what is the future, how you are going to participate. Once I finish up, then Arnab will take over. Arnab Das is a person who is the lead developer in AIORI. He will take you through some of these concepts which are listed here. And remember that these are the concepts which in turn you will have to use when you are doing the workshop at your end in your institution. Now, once he finishes, then we have a quick overview session on measurement platform by Andre. She is also a part of the AIORI team. And then we have some time for Q&A, and we will try to answer as many questions as we can within that time frame. So with this, thank you everyone once again for joining this repeat session, and over to you, Anam, for taking the proceedings forward.
Thank you for the introduction, sir. And thank you everyone for joining this program. Starting with the internet, when we talk about internet, I think it is very much important for us to understand the history of how internet came to be what it is now today. So when we think of the internet is basically a planetary scale way of communication, right? So we are sitting in our home and we are able to communicate with someone who's sitting in the opposite side of the globe, right? We are able to access content, access resources from different places, right? So I'll start with discussing the history a little bit. Moving forward, I'll talk about the internet architecture, the infrastructure that maintains the entire internet that we use, and the governance that is necessary to maintain this huge infrastructure. And finally, I'll end with a little discussing a little bit about what we do at IIRI. So, for the history, it was 1960s, and it had been 15, 20 years. The World War ended, and everyone knew that the information is what will let the countries prosper. Information is what they need to focus on. So, uh, ARPA, Advanced Research Projects Agency, which was directly under DARPA, US government, they started discussing a concept of universal networks for sharing the compute resources they had in different organizations and different institutions. Also, the same time as the telephonic network was becoming mature day by day, the circuit switching that was there in the telephonic networks, the idea of circuit switching was gradually starting to get adopted more and more by people in other domains as well, which led directly to the idea of packet switching that was discussed in ARPA again. So, in a few years, they created a small kind of a POC with four different institutes. They created ARPANET in 1969, where they connected the networks of four different institutes, two University of California institutes, and one University of Utah, and one Stanford Research Institute. So this was basically the early research that they were doing to create a worldwide network for resources. This is basically the early internet days. Internet was not still not a concept, and this is basically what we can call a forefather of internet. So in 1969, they created this small network connecting four different sites, and in 1974 they published their studies in Internet Experiment Notes. This study was basically how this interconnected network could function, and this is where TCP/IP stack was discussed the first time. So this four node network, when they are like connecting different sites, it is like more and more institutes started connecting their networks together, and this ARPANET started uh, growing in a really fast rate. So it becomes harder and harder uh, to remember which IP belongs to which network, which IP belongs to which server. So Stanford Research Institute, one of the initial institute in the ARPANET, they started maintaining internally a file called host.txt. And there they started mapping IP addresses to the host names. So these host names, we as human, we are more familiar with host names, and we do understand host names. It is harder for us to remember IP addresses, right? So IP address is the address of some device in a network, and uh, this is basically numbers, and systems are really good when good to understand these numbers, right? So what Stanford Research Institute did was they started maintaining a hosts.txt file which mapped these IP addresses to host names. And this idea was being started being adopted by more and more people. Uh, People started exchanging this hosts.txt, and soon it became a big bottleneck because the size of the file became too big to maintain. So in 1980s, in 1983, John Postel, who was one of the key pioneers of internet, uh, he was he was one of the maintainers for host.txt, and he distributed these files, and he asked Paul Mockapetris to find a compromise between some alternatives that they have. As this host.txt file was becoming too big of a file to share with different institutes, they wanted to create something that is more dynamic, that is more easy to maintain. And that is when Polymer Queries created DNS. So RPass started researching in packet switching, which resulted in the idea of TCP/IP. And once the network starts getting bigger, they had to manage a file mapping the host name to the IP addresses, and that resulted in creating of the DNS protocol. This both TCP/IP stack and the DNS protocol, these two protocols are the main uh, main ingredient of the internet that we use today. Everything that we do depends on these two things. So the entire internet depends on two things: the names and the numbers, the IP addresses that maps each and every system that is in the internet with a unique IP address. A lot of times it may not be unique, but each and every system has some IP address, and the names that we as a human we are more used to. We as a human we understand these names better. We can memorize this name. As a human, we won't be able to memorize numbers like 103, 149, 148, 147, but it is easier to remember google.com or iphone.net. Right? So the internet is based on these two things: the names and the numbers. The numbers are the IP addresses, the names are the domain names or the host names. And the numbers are not just the IP address, but there are a lot more numbers that is being used internally that we often skip. We skip it in our curriculum, we skip its discussion just because it is not visible. So, for an example, UDP is one of the packets that uh, supports then supports the DNS protocol, and that it inherently supports the entire internet in uh, some sense. So, this UDP packet is represented by the number 17. The TCP packet is represented by the number 6. ICMP packet is represented by number 1. So these numbers as systems servers are so good with these numbers. They can interpret these numbers properly. Everything we represent, uh, everything we use in the internet in some way are represented to numbers. And then for the human part, we have the host names. In a small network, when we try to build a small network in our home or in our lab, what we usually do is we let's say we have multiple different devices: PC1, PC2, PC3. We and if we want to create a network out of these, we take something called a router and we plug in the different systems in the router, and we usually are able to communicate from one PC to another. Right? The communication again works on top of IP addresses. So three different PCs will have three different IP addresses, and using this unique IP address of each and every device, we can communicate with them. Uh, Now this setup is seen in a lot of places. This setup is there in our home routers. This setup is there in our university labs. Is this is even somewhat similar setup is there in the ISPs as well. But this is a very small network. This is a local network that we are speaking about. To create internet, we need more local networks. We uh, assume that there are everyone has a local network, and we will try to connect these local networks. So if I have a local network in my home, if someone has a local network in their university, I should be able to access the resources in their university, and they should be able to access resources in my home. Right? So these two local small networks need to connect with each other. So what we do is we connect the routers with each other and do do the networking and configuration appropriately, so that when there are two different systems connecting two different router devices, uh, one of the router is able to communicate to the another. One of the routers can able to connect to another router, and one PC is able to communicate with another PC. And to facilitate all these things, what we need to do is we need to have some exchange between the routers regarding what IP spaces they have access to and the IP routes they have access to. So there comes this. So we can represent the previous diagram with this is a bit more visually uh, attractive diagram. So let's say there are four different small and medium-sized networks, and we are connected to one of the routers in this red network, and we want to access some resource in this yellow network. So for us to be able to do anything, first we need to know where this yellow network is, and for that what needs to happen is there needs to be some exchange of information between these different networks. The information that is exchanged between the networks, it is the IP routes, and the protocol that facilitates this entire thing is called BGP, or Border Gateway Protocol. So once the route is exchanged between each and every router and between the networks, what happens is now all the networks have enough information to make this decision. So whenever we try to communicate from S to D, we want to send a packet, we want to access some resource, we want to read some, let's say, Wikipedia article. So now router 1 knows that the best possible way, or one of the best possible way to reach this D is to go to R4, the router 4. And from router 4, it will go to router 5 to router 6, router 6 to router 7. So the entire internet that we are using is basically some packet, some data hopping from one network to another till it reaches the final destination. Now, this hopping of networks is exactly what we see when we use a tool called traceroute. Traceroute is a tool that is usually available in both Linux and Windows. In Windows, it is called traceRT. So here, uh, I have run the traceroute tool and given it some IP address. What the tool does is it maps all these intermediate hops between routers. So as you can see that from my network to reach this IP address 142.250.183.142, this is an IP address of NTA, National Test NTA, the government unit of NTA. So this is the public IP address of their website. And to reach this IP address, there are 14 different hops that a packet has to meet. So there are 14 different routers from which my packet is being routed through. This is how the internet works in general, but this, as you can see, it is kind of a bit inefficient when we talk about ingesting some content. If it is farther than us, then it will take a lot more time for us to get that resource, right? So if the content of Wikipedia is stored in USA servers, it will take us more time from India to access those servers and read Wikipedia, whereas people from US will be able to read it faster because they are near to the network, right? So nowadays, what people do to like remove this dependence of so many nodes is they bring the content that was served from some data center in probably in USA uh, into the nearest data center or ISP or the nearest location from where you can access the content. So previously, if say a website called cloudflare.com. It took 200 milliseconds to open because the main servers are somewhere in US or in Europe or in Japan or somewhere. We can cache that in our nearest data center, and from the second time we open cloudflare.com, we won't have to wait 200 milliseconds, but probably 30 or 50 or 70 milliseconds, and we can get the data from the nearest location. So this is called edge computing, which people are adopting more and more. This is there are dedicated research organizations that do research on just this particular thing. This is how CDNs work. Every time there is a match somewhere, uh, there is some movie premiere and people start watching them in OTT platforms. We do not ingest the content, we do not watch the series, the movies, the uh, live matches from the actual server, from the actual location where it is stored, but all the entire data is being sent to the nearest server, nearest data center to us, and from there we ingest the content instead of asking directly the main server that give me this content. So this is one optimization that is usually done. This is and this is done very often. Each and every OTT platform that you use this kind of edge caching. Moving forward, there was another part that was the DNS. So previously, all the routing and everything was based on the IP protocol. It was one layer of the TCP/IP where uh, the routing is concerned. Moving forward, we also need to have host names associated with these IP addresses. Otherwise, for humans, it will be really hard to uh, go to google.com every time because we need to remember the IP address. So the DNS protocol that Paul McCarthy built back then was based on a few concepts. He built a hierarchical architecture for the entire data of DNS, the mapping from domain to IP address or host name to IP address to be distributed among different hierarchy and distributed in uh, sense of demography as well. So whenever we open a domain, let's say example.com, we are not connecting to example.com directly because we know example.com, but our systems do not know what example.com is or where the server is. The system knows how to route the IP, not the domain names or the text or this host name, basically. So our system will do a DNS query to something called a recursive resolver, which will give us the answer where example.com is. So this DNS and the host.txt, to be more precise, host.txt file, which was maintained by Stanford Research Institute, that was very similar to a phone book. Now, what happens when there are many numbers, hundreds of numbers, or thousands of numbers in a phone book? It gets really hard to distribute. It gets really hard to find a phone number in that phone book. So, in the DNS architecture, we do not have a copy of the phone book, but there is some system that can do some operation and it can still find uh, the IP address that is mapped to a host name directly. I'll come to what the phone book idea has changed into uh, in a while. So usually when we open something say example.com, we are first requesting for the IP address and then we are connecting to the IP address. So this happens for each and every resource that we open, each and every content, and for each and every web page there are multiple of these. So this is multiple of the multiple URLs that are being called, that are being connected to, and multiple DNS resolution that happens. In case of wikipedia.org, if I open wikipedia.org in my system, same thing will happen. My system will ask some recursive resolver what is IP address of wikipedia.org. it will return the IP address, and my system will then connect to that particular IP address. Now, Wikipedia, now even for some central server, searching for wikipedia.org in a big pile of host name and IP address mapping will be really hard. Right? If I give you a big file and I ask you to search for one particular number, it will be really hard. Right? So the DNS architecture, the DNS protocol that was built in a hierarchical manner such that the search of the IP address becomes easier. So whenever this wikipedia.org query is sent to a recursive DNS resolver, what it does is it first somehow gets the IP address of org.org, and then it asks the IP address of .org. That's a completely separate server. It asks that server, where is wikipedia.org? Then it gets the result where wikipedia.org is, and then if it is en.wikipedia.org, it will ask where is en, and if it is www.wikipedia.org, it will ask where is www, and so on. So this is the hierarchy that I was talking about. But even in this hierarchy, you can see that we started with an assumption that it will somehow get the IP address of .org, right? This IP address 199.19.56.1. This is the IP address of the org DNS server. So how will the server get the IP address of org DNS server? It will ask 13 different root servers. So this is basically what was happening in the previous slide as well. So this simple uh, design diagram is basically representing this complicated thing where there are 13 different root servers. So these are some servers that can be treated as constants, that already have constant IP addresses. These have uh, the mapping that usually do not change very often, and they point to these TLDs, top level domains like org, .in, .com, .net, .info, .sh, .ai, .io. So these are the top level domains, and these root servers only know where these top level domains are. Once we get the IP address of the top level domain, we can ask the top level domain for the IP address for the second level domain, or wikipedia.org. So each and every layer of this hierarchy are bounded by their own authority. They know one thing and they know it well. They don't have the mapping to everything. So these servers are called authoritative name servers. So if let's say there is some university website called let's say uh, Calcutta University edu.in, suppose. So the root servers will not know what is the IP address of this domain. Root server will know where .in is. .in will know where edu.in is, and edu.in will know where Calcutta University.edu.in is. Same goes for say Chandigarh University. So edu.in is the server that will know where Chandigarh University.edu.in is. So these are the main components of internet. So internet depends on two things very often, that is IP and DNS. IP again depends on BGP to share the routes and other information. DNS is comprised of two different servers. One is authoritative and one is recursive. Authoritative again depends on root server, TLD, and SLD, and this recursive server queries the authoritative server and provides us with the results. So recursive server is basically uh, querying all these servers in our stead and giving us the answer. So all these things that I'm talking about, these are uh, theoretical and protocol level things. These are the softwares that make the internet work. For the software to run, there needs some hardware, there needs some connectivity between different sites, there needs to be connectivity between different networks. So moving forward, I'll talk about a little bit about infrastructure and a little bit about security. All the countries are connected, and all the networks as well are interconnected by uh, these submarine cables that connect two different countries. So any country that has access to a ocean, that has a shore, uh, it is highly likely that some there is some submarine cable that is connecting the entire internet to that country. So this is, in some sense, this is what the internet looks like. uh, so here in India, you can see that there is some hub for the submarine cables at Mumbai. There is some hub at Chennai. So this is the place where the submarine cables come in, and this is the place from which uh, we as a country are connecting to the rest of the internet. Moving forward, root servers, the DNS root servers, the 13 root servers that are constant, that is also what the internet depends on a lot. Whenever we want to do some query, some DNS query, we want to open some website, we need to have access to the root servers. Only then the entire hierarchy can be traversed and we will get the final answer of the final IP address for us to connect. There are, as I just said, there are 13 root servers, and all these 13 root servers have copies distributed over all the countries. So India has a lot of copies, Africa has a lot of copies, uh, Singapore has some copy, US owns a lot of these root servers, plus they also have a lot of additional copies as well. Australia also have a lot of copies. So all the countries have some copy of these root servers with them. Whenever we try to traverse the hierarchy of the DNS, we usually query one of these copies of root servers. The way these servers are deployed, the way the servers are connected to uh, the network of that country or that demography is in a fashion we call anycast. So anycast is a way where there are let's say there are two different systems that are connected to a network, but both of them has the same IP address. So IP address is, as we have read, IP address is a unique address of a system in a network. Right? But what happens when two different systems have same IP addresses? That is a scenario that we call anycast, where uh, based on where we are, based on the routing, based on different parameters, our packet and our connectivity we can connect to the nearest uh, IP address, nearest server that is announcing that IP address. So all these root servers have all the let's so 13 root servers. The A root server have all the A root server copies have same IP address. All the B root server copies have same IP address, and so on. Now, all these things that we are talking about, these things connect people from one end of the planet to another. But we also need to ensure that the connection is secure, right? For an example, most of the websites that we open nowadays have SSL certificates. Most of the uh, websites we open nowadays have TLS 1.3 or TLS 1.2 at least, right? So at least the content that we are ingesting has some form of security in them. But these are all at the application layer. Down the layer, when we talk about the BGP, when we talk about DNS, these are the protocols that run the internet, not just encoding the content, but run the actual internet and connect two different systems and two different networks. Right? So these protocols also need some kind of security considerations. So there are some protocols like DNSSEC that uh, cryptographically signs the DNS. There is RPKI that ensures that not everyone can announce an IP address, because if we can announce some IP address from two different locations, then technically I can announce Google's IP address from my home as well, right? There is no one stopping me from doing that. So RPKI, and there are some other protocols as well, security protocols that ensure that I won't be able to do it. The only problem is that TLS and SSL, these are much more widely adopted. Uh, any and every security protocol that exists, if it is in the application layer, it is widely adopted. Whereas in case of uh, RPKI, in case of DNSSEC, these are, although these exist, these are not widely adopted because of awareness, because of uh, right skills and maintaining the skill, maintaining these uh, DNSSEC servers, and maintaining these DNSSEC signatures. So the submarine cables and the root servers that I discussed, they create the entire internet, and the protocols underlining like DNS and BGP, although they have security considerations, but the security considerations are not widely adopted. This is a big field of research, and different groups and different research institutes are still researching on how to make it more secure and adopted as well. So this gigantic planetary scale network of connectivity needs to be managed. Otherwise, it is working now, and probably in 2 more years, I see that there is no internet connection in some areas. In 5 more years, half the planet doesn't have internet connection. So these things need to be maintained, these need to be managed properly, and these needs to be governed properly. So moving forward, the governance. The governance For the governance, there are a few different organizations that manage whatever goes on and the internet and how the internet works. One is ICANN, one is IETF, and one is IANO. ICANN majorly works on the policy side. IETF works on the engineering aspect, and IANA acts as a registry for all the names and the numbers. And all these three are jointly funded and, in some sense, even governed by something called an Internet Society. So, this ICANN and IETF, who are these? These are engineers, these are developers, these are uh, mainly people from the technical background, coming from different organizations like Cisco, Juniper, Huawei, and others, coming in like coming in the ICANN's annual meetups, IETF's annual meetups, and then discussing how the internet, how the networks are working properly, what are the problems that they are facing, and how they can be solved. ICANN, although works on a multi-stakeholder based architecture, IETF, on the other hand, tries to find a rough consensus of all the engineers and the community in general. So all the protocols that are being developed, they are being developed at IETF, and the policies of how something would work, uh, what kind of data should be retained, how the domain names can be allocated and the IP addresses can be allocated. The policies behind them are discussed in ICANN. So I'll just give a quick example. There is a protocol that people are discussing a lot in both IETF and outside. A lot of web developers are even discussing it. It's a protocol called Quick. So Quick is also, people are also calling it HTTP 3.0. And this is a protocol which is very modern, and it is actively been discussed in different forums for the replacement of HTTP 2.0, because it does have a lot more uh, operational considerations, and theoretically it is more operational. So IETF is the main body that is standardizing the Quick. IETF is the main body that is building the Quick protocol, basically. Moving forward, after after ICANN and IETF, there is IANA, which acts as a registry. So this is a screenshot of the IANA website, where there is data for the root zones or the root servers. IANA manages all this data as a registry for both the DNS and the IP address. So this is the screenshot for the DNS. This is the screenshot for IANA managing the numbers for the protocol. So you can see here IPv4 has a number 4. There should be TCP somewhere. Transmission control TCP. This is number 6, and UDP is assigned number 17. So whenever if you ever see a packet, and in the fields of the packet you see that for the protocol identifier there is the number 4, so you will know that is an IPv4 packet. If there is the number TCP, if it is number 6, you will know it is a TCP packet. IANA maintains these as well. Another thing that IANA maintains is the RIRs, that is the regional internet registries. So RIRs, there are under INA there are 5 RIRs. They are the APNIC, ARIN, LACNIC, and RIGE-NCC. So what are these, and why do we need them? Why were they created? So whenever we are talking about internet, we need some IP address for ourselves so that we can have an identity in the internet, and after that we can connect to some other system around the globe, right? That IP allocation to different ISPs, to different organizations in different region is handled by these RIRs. So if you uh, have a website of your own, the website will have a IP address, public IP address, and that public IP address will be allocated by APNIC or someone below APNIC. Uh, every organization, every education organization, and every other organizations as well get their IP address allocated from somewhere, and usually these RIRs are the one who maintain those. So ICANN and IANA is the main body under which these RIRs function. Under these RIRs, there are national registries. For an example, Japanic is for Japan, most probably. In India, we have Nixie. In China, I think it is CNNIC or something like that. So these sits directly under these RIRs, and under these national registries, there can be other local registries, or there can be other ISPs who provide you with IP addresses. So as an end user, we get our IP address allocated from either of these. It can be either an ISP who is providing us with a public IP, or some local registry, or the national registry of that country, or it can also be the regional registry as well. So this Internet Society kind of manages the IETF operations, ICANN operations, and IANA operations. ICANN and IANA maintains the registry for RIRs, root servers, and these RIRs then again maintain NIRs and other local registries. This is how the entire internet is governed. In future, if a protocol, if you hear about a new protocol, it is probably IETF that built it as a standard, ICANN who made the policies around it, and in IANA you will be able to see the numbers that are allocated for it. Moving forward, what we do at IORI regarding these uh, protocols and this internet's architecture. We work on most of our works can be divided into two of these uh, parts. One is internet infrastructure, one is measurement and analysis. For internet infrastructure, we research on resilient DNS implementations. We try to implement more PQC algorithms in different softwares like in DNS servers and other servers. So PQC stands for post quantum cryptography. We also try to find the exact location of IP address from where it is announced and the discrepancies between uh, what people know is the location of the IP address and where it's actually being announced from. So these are some of the verticals that we work on, that we research on, and all of these works are closely tied with IETF, ICANN, AppNIC, because these are the organizations that are governing the internet. So we work hand in hand with them. We uh, ask for the latest research for how things are happening in other places and all. So these are some of the things that we work on currently. Second part is measurement and analysis, for which I'll kindly ask my colleague Oindri to come and explain a little bit about what we do in measurement and analysis.
Thanks, Arnav. Please let me share the screen. Okay,
Sure.
sharing is not turned on. Please grant me access. Srijit, if you are there.
Yeah, access has been provided.
Okay. So thanks, Arnav. So I think by now we have gained insights on how internet functions. Now we will shift our focus to how we measure internet and why we measure. So starting with how we measure internet. So this is our anchor network. Okay, so what we call as anchors. Anchors are basically Raspberry Pi devices. Okay, let me share the yeah. So anchors are basically Raspberry Pi devices. So with that, it needs inside this box. There is a Raspberry Pi a device, and we provide power adapter and an Ethernet cable. So to connect this, we need internet connection and electricity for connecting it. So once we connect it, and in this Raspberry Pi device, we have installed one code. Okay. So what we do, we have our portal, we send the request to this particular device. This device executes that command and then backs us the response. This is how it works. And this device is deployed throughout India, like over 300 plus anchors are distributed throughout India. So these are the places. So if we look at the matrices of it, in Eastern region there are 56 of it, in Western 12, Northern 27, and Southern 60. So this is how we are measuring various parameters of internet like ping, then DNS query, then trace route. So first coming why we are measuring it. Basically, we are measuring it to based on the data that we are getting. We analyze it. Researcher uses this data for their research purpose because for like we can identify from where is the delay originating. Okay, so there may be a DNS issue, there may be a network congestion. So we can decide based on the data that we are getting, based on the evidence, we can decide our next actions. Okay, suppose if like in the morning for google.com or for aiori.in, I am running a latency check and then I am getting there that 12 ms is coming. Okay, when I am executing this scene in the evening, I'm getting 32. So I can see that, okay, it's in the morning, it is performing better than the evening. So I can compare the result. So basically, we can compare the result across targets and conditions. Okay. So that is how like we are measuring and why we need the measurement data. So starting with, so basically how this are getting deployed, as I mentioned, uh, we need to connect this on a Ethernet cable. Means we need to give a internet connection and electricity for turning this on, and then in our portal we need to register this anchor. When we provide this, at the back of it we provide a QR code. Scanning that QR code, we need to register this. Once this that particular anchor is registered, like here you can see that there is a choose file option. We need to upload that keyword and please the anchor location. We need to enter the location, okay, where it is getting placed. So once you register, the anchor is like the anchor is on. Okay, it is online. So we can like sitting remotely. I'm sitting at Kolkata and you are sitting at Odisha or Kerala or Bangalore. Then I can through our portal I can access that anchor and can execute some measurement from that anchor. Okay, so just to mention that this is not in our student workshop. This is not a mandatory thing. If you want to host an anchor, you can, but this is not a mandatory thing. I'm just explaining these things just to let you know how we deploy these anchors. So what is there in these anchors and how we deploy it, how we make it online. Okay, so let me start with a latency check. For suppose for google.com, I am doing a latency check and I will check like throughout India from our anchors what are the latency coming and what is the network performance currently. Okay, so here we can see that from Chandigarh location, the anchor we have in Chandigarh connected to this ISP. The RTT average is coming as 31.54, where comparatively Greater Noida has a lower than Indore, Jaipur, Kolkata, and this is the metrics that we are getting. Okay, so you can see, you can filter it from here. Like less than 30, we have two places, one in Jaipur and Haryana. Okay, So if the website is pingable, then you can test your own institute domains and check the latency, like from our anchors, what is the latency coming and how it is performing. Okay, latency is the time it is taking to it measures the time for packets to a specific website and back. Okay, so that is what we are calling it as latency. Second is, as Arnav already mentioned about the root servers. Okay, so what we are doing it over here, we have 13 root servers. We are continuously monitoring it through our anchors. Okay, so you can find in INA.org, as Arnav already mentioned, that these are the root servers. Like INA is responsible for setting up the IP addresses. So these are the IP addresses. So what we are doing here from the background, we are basically just pinging this IP address from different anchors that are hosted throughout India, and we are generating average result from various places. So this is the latency that is coming. And this is basically, this is the total of all the 13 root servers. If you check individually, like starting from A to M, L, you can find each latency, how it is performing. Okay. So this we are regularly firing these endpoints to measure the RTT. Next, we have AIORI clusters. So AIORI clusters means these are the we have 10 nodes. One in Chandigarh University. Next, we have in Purnima Institute of Engineering and Technology, DY Patil University. Then we have in IISc Bangalore, Sri Sri University. We have in IIT Guwahati, and 4 places in Kolkata. That is, one is in Shibpur, Indian Institute of Engineering, and then Basis Technologies, IEM Kolkata, and in STPI. So these are the 10 nodes. So what we are doing here, we are just on regular basis, we are just pinging the node endpoints to measure the latency, and by that we can reveal how each ISP is behaving. Okay, so if I check on to this, like INV2 236, which is in Kolkata, and it's continuously pinging Chandigarh University's node. So this is the network performance. We can see that like the on 24 5 2026, like on May, the latency for 47.736. Then it comes today, like not today, yesterday it 33.2525. So this is how we can track how the ISPs are behaving. Okay, so these are the things that we have. And yes, like based on the outputs that we are getting, we can prepare some evidence to support ISP escalation onto this. They can work on it and they can improve if they want. So these are the data that we have been generating through our platform. Next, we have our AIORI tools, that is check your website latency, that I have already shown. Measurement portal. Okay. So coming on to this measurement portal, we will be conducting some practical measurements and experiments on our next session, because that we want the students to go with some to go with some experiments, hands-on experiments. Okay, they will uh, do some experiments in this platform. They will run some measurements from here, and they will generate some reports, analyze it. Okay, these are the things that we will be showcasing you on our session 2. Next, we have DNSVs. So I will request Aditya from our team, if you can walk through this DNSViz portal and RPKI Viz.
Yes, can you please open the DNSWiz website?
Yeah.
So, this is a tool which visualizes the health and security of the domain name system, especially in this DNSSEC measurement uh, tool. We can check the uh, website uh, that the website is fully DNSSEC signed or not. If you can launch this tool and try to test for some website, it would be great. It validates the trust chain, detect misconfiguration, and the overall reliability of the website. Single domain scan. Let's try for AIORI. Yeah, so it provides us with the detail of the whole trust chain if it's fully signed or not. And go to the previous page. There was one more tool. That was DNS resolver management. Here we constantly checks that we continuously test from many.
Your voice is breaking, Aditya.
Okay, for the moment, I'll take over Aditya then. So, in this DNS analytics, DNS measurement, what we are doing is we have listed down the DNS servers of different ISPs and DNS servers used by different networks, and we are constantly measuring the service, the quality of service, and different other parameters of this DNS server, so that we can check how many DNS servers are supporting things like DNSSEC, what is the average latency for the DNS servers, what is the uptime for DNS servers, what is the reliability, then there are some other parameters as well. So this gives us a greater view of the kind of DNS infrastructure we have in India. We try to measure as many DNS recursive resolvers we can find. If there is some DNS recursive resolver that is not here that you know of, you can send us the IP address and we can add that here as well. Uh, so this gives us a bird's eye view of the entire DNS infrastructure of India, basically.
Now coming on to this root server visualizer, as Arnav mentioned, there are 13 root servers, and for all, this is a global DNS root server visualizer. So here we can find the total instances and sites we have. So if I filter it for Asia, India, then you can see with us we have total 43 sites and 63 instances. Okay. So this is the data that we can provide. Okay. Now coming on to IXPVs. IXPVs basically provides a global matrix of total IXPs, ISPs, and facilities that we have. So I will request Debayan to just give a walkthrough of this IXPVs portal.
Thank you, Andre. So please go on this portal. So as Arnav said that we are connected through internet, but how networks are connected? Networks peers each other. Pairing means two networks will give the IP route to them and expect that two can be connected with each other. Also connected with the transits, the other ISPs, IXPs. So what is the IXP? IXP is a internet exchange point where all transit CDNs, all ISPs, some big ISPs or small ISPs came and peers with each other. So this is global IXPs. It is connected with peering DB. So the data which this portal is showing, it is for peering DB. Peering DB is a publicly available ISPs database where ISPs and IXPs, everyone come to that portal, give their information for any important purpose and any connection specific purpose or stakeholding purpose. So you can see the IXP count by continent: Africa, Antarctica, Asia, Europe, North America. Can you please tap on this Asia? Okay, okay. Uh, go go back, just back to global and just go to Asia. So for the subcontinent Asia, you can see the Indonesia, the country's IXP frequency or IXP's count. You can see that Indonesia, India, China, Hong Kong. So please can you uh, tap on the India bar, this India bar. So here you can see the number of IXPs in India. There are currently 40 IXPs in India. Some are very big ISPs, but some are very small IXPs. Like they have many many small capacity, many small connections. So can you please tap on this total IXPs in India, please? So here you can see all the IXP's details like Day 6 Mumbai, Nixie Delhi, Extreme IX Mumbai. So uh, there you can see that the highest capacity uh, IXP is Day 6 Mumbai, which have 448 peers. So you can see the peers also here. PCH, AS42, Cisco systems, they are all our network organization, ISPs, CDNs, like CDN Apple INC is connected with that IXP. Can you please go to the Netflix? There is Netflix somewhere. There, yes, just go there. Just go there. Okay. So the ASN of Netflix is 2906. The Internet Exchange, it is connected with, you can see the Internet access name. It is globally connected. So this has many IXPs whole in the whole world connected with Netflix. So there are also facilities. Facilities mean for the many of the facilities term is it is physically present somewhere. Like if you have to connect with any IXPs or any ISPs, not in case of ISPs, for peering with any IXPs, you have to present in somewhere physically. So the physical location here is the facilities. You can name it data center also. So can you tap the know more about this ASM?
Yeah, Devan, I think we'll have to stop here because we need some time for Q&A as well. So
Okay, sir.
So at this point in time, before Devan continues, does anyone have any questions? You can raise your hand and ask the question when it is your turn. Yes, Dr. Lokesh Pawar, you can ask your question.
Yeah, very good evening to all of you. Sir, there is one question about this. This AIRE, they manage everything. It's a complete Hawkeye on the all of these ISPs and all these service providers, whosoever is giving service in India. So we can keep a check on every ISP with this AIRE.
Yes, we can. Uh, the larger the deployment of the anchors, that Raspberry Pi devices, the more granular information you will get. With the current spread also, uh, we do get a decent amount of information. But if there are networks where this Raspberry Pi or anchors are not present, then we will not have any information for that particular ISP.
Oh, thank you. One more question,
Yes,
sir.
please.
If we can see their performance and how the latency is taking place in between the networks and what is actually happening, we can see, and what else we can do, the way we can help them, or why we are doing these things, what is the motive behind, and how we can help them, or we are not able to help them, we are just to keep a check on it.
No, no. So there are two, three different dimensions, Dr. Lokesh. Yeah. Okay. Uh, the first dimension is that we want to have a macroscopic insights on how the internet is behaving uh, in our country. So that is what uh, is the first objective with which we started. Okay. Now, going when we started working on um, it, this measurement cannot happen in a standalone basis. So the entire data which is getting generated, not one organization can digest it and look at it. So the second objective with which the motive, as you say, is to have a collaborative environment in which the data, whatever is getting collected, it is shared, it is analyzed, and the results are shared with the larger uh, community. The third is to inform the on the public policies, and that is, I think, where your intent is, that what we do with it. This measurement data we not only collect and share the analysis with the ISPs, but we can also share with the government itself, so that effective public policy decisions can be taken based on the real measurement data. Now, are we covering the entire network, each and every network? No, it is not. Because we don't have that kind of spread with anchors. We want to reach there, but the way things are progressing, we may take some time, wherein every network in India is having at least one of our Raspberry Pi anchors. Then we can very comfortably say that yes, we can give a macro hawk-eye view of all the networks in India. But till the time it doesn't happen, we can't say that. But it is a uh, assuming that whatever we have and it is a representation of the entire nation, we can give some certain amount of high level macroscopic insights. That is one. But in the context of your academic institution, the way it can be used is that if you are, say, taking from an ISP 20 Mbps lease line or 100 Mbps lease line, okay, you can use this measurement system to see that how that exactly it is performing, whether it is giving the right kind of bandwidth throughout the period. Now, whenever we have talked with academic institutions, we have found that there are generally um, constrained with bandwidth availability during the daytime when the students and teachers and everybody is present, but in the night, that is absolutely fine. But if you are having a hostel, then there is also a bandwidth constraint. So those kind of constrained places, we can put an anchor, see that what is actually happening, where is the where is the demand for the data, and uh, what kind of latency you are getting. And if it can be improved, it will overall improve the situation of internet availability in your institute. So that is a very local application, but that is what can be done.
Thank you
Does
so
it
much,
make
sir.
sense?
Yeah. Thank you so much. It was very much informative, and I definitely it opened some of the more places and points to think about these things. Thank you so much.
Thank you, Dr. Pawar. Any other questions at this point in time?
Hello, sir. May I?
Yes, please.
So this is Dr. Vikas from Pune. The tools
Yes,
that you
Dr.
have
Vikas.
mentioned, the tools that you have mentioned now. So whether these tools we have to elaborate to students in workshop, or whether you will provide us material on this so that we can explore these tools in better way.
Yes, we will be providing a material on like the full platform. We will be providing AIORI handbook to you,
Okay.
to all the
Thank you.
faculties.
Yeah. So that means it will be a part of your our workshop where we have to taught.
Correct.
Okay. Thank you.
Hello.
Any other questions?
Yes, sir.
Yeah, please.
So may I?
Yes,
Thank you so
please.
much, sir, for
Go ahead.
this session. Yeah. Sir, I just have one question. Can we access the recording of this session somewhere online? Uh,
Yeah,
is it
yeah,
possible
it will
to
be.
access the recording?
It is getting recorded and it will be available on our channel. Once this session is over, I will request Srijit to upload the recording and share with everyone.
Will it be on YouTube, sir?
It will be on
Yes,
YouTube.
yes.
Okay, ma'am. Thank you. Thank you so much for the session.
Sir, I have a query. Hello, good evening, sir. Hello.
Yes, please.
Yeah, I wanted to understand the difference between AIORI network and AIORI clusters. Because on the map, we have a lot of nodes shown when we are clicking AIORI network, whereas when we click on the clusters, we have only like you showed like 4 or 5 clusters only. What is the exact difference in them?
Yes, basically this is our anchor network. These are the Raspberry Pi devices on which we are sending the request for executing the commands. Okay, and AIORI clusters means these are servers like what we are calling as nodes. This you can consider as hub centers. Okay, we have 10 nodes all over India as of now.
So to give a little bit more idea on what these nodes are, we so anchors are the devices from which we are firing the measurements, whereas these 10 different nodes, these are some of the services from Ivy, like the DNS service that we are developing and some other services. This is where they are announced from. So we are also announcing a DNS server from all these 10 locations. We are announcing a lot more measurement measurement services from these 10 different services, different nodes basically. These are basically a pack of a server, router, a switch. So this is basically kind of a small data center. These are is academic institutes that that have let us keep our servers there and uh, host the services from that network basically.
Understood. Thank you so much.
Thank you, Tejashvi, for that question. Any other questions or comments? Okay, hearing none, I think we are done with our session for today. This was the repeat session which we did initially on Wednesday, and today it was a repeat session. Thank you all for attending. The second part, which is uh, wherein we will take you more deep into the measurement and how it will be used when you are conducting the workshop at your institution. With all those information and how the measurements will take place when you are doing the workshop, how the data will be recorded, what kind of report you can generate instantly, and what is the report which we will see together. So, with all those information and much more practical and some with very deep macro insights. We will come back to you on Wednesday, which is on 22nd. And if some of you could, who will miss for some reason the 22nd, there is a repeat session which is going to happen on next Friday on 24th. You are most welcome to attend that as well. So today, we have finished the first part, which was more theoretical in nature. Now, the second one is going to happen next week. So, thank you so much, everyone, for attending this repeat session, and we will see you next week, Wednesday. And thanks to Arnav, Andri, Deva, and Aditya from India Internet Foundation's team for uh, giving us, taking us through the entire thing. And thank you all for attending today's session. The meeting is adjourned.